consider spring potential energy. Remember I said we will learn two types of potential energies. We already looked at gravitational potential energy. And we're now going to look at the second type of potential energy, which is spring potential energy. There are also other types of potential energies, but we will not be considering those. We're just looking at mechanical stuff. So we have two things to consider: gravitational potential energy and spring potential energy. When you compress or expand a spring from its natural resting length, then you store energy in the spring. The spring stores energy. You do work to compress the spring. That work gets converted to potential energy stored inside the spring. When you release the spring, it springs back using that energy. So that energy is converted to kinetic energy and it springs back. Similarly, exactly the same happens when you expand the spring out. Then also it has moved from its normal resting length and it stores potential energy. You have done work to pull it out. As soon as you let go of the spring, it bounces back to its resting equilibrium position, and it uses the stored potential energy to convert to kinetic to be able to move back. Okay? So a spring has a particular spring constant, typically written with K as the symbol. This depends on the material of the spring, how stiff it is, and how long it is, etc. So that's just a constant for a spring. A spring typically obeys this kind of force. It's called a Hooke's law or a Hooke's force. Basically, there's always a restoring force in a spring, which is opposite to the displacement of the spring. So if I have pulled the spring out from its normal resting position, so it's now its length is longer, then it's trying to return to its normal equilibrium position, its resting length. And as soon as you let go, the force will make sure that it comes back to that resting equilibrium position. So it's in the opposite direction of the displacement. Whereas if you had compressed the spring from its normal resting length, then the force is such as to drive it back to its normal resting length. So that force is always in the opposite direction to the displacement, hence the negative symbol. Okay, so negative, make sure that the force is in an opposite direction to x. Remember, both of these, x and f, are vector quantities. K is a scalar quantity, it's just a number. So this F is known as a restoring force. It always wants to restore the system to how it was before you changed anything. Okay? So a spring must obey Hooke's law in order to work properly, otherwise it breaks. Okay? Let's say this is the normal resting length of the spring, then its displacement is 0. Okay? Now if we take a block and we push the spring so that we compress it, we have to do work, yeah, where the force that we apply times this displacement here is going to get me that work done, yeah, and that work is converted into potential energy for the spring, and the formula for that potential energy in the spring is half kx squared. Okay, since nothing is moving here, kinetic energy is 0. As soon as you let go, so you remove the force, the spring will use the restoring force to bounce back to its equilibrium position. Yeah, it'll push the object out, and at equilibrium position, once again, it stores no energy, so its potential energy is 0. It has all the energy is converted back to kinetic, so it's half mv squared, which was the formula for kinetic energy that we saw earlier. Okay. So a little bit of an explanation is required here about that half kx squared, how potential energy is half kx squared. In the case of the spring, you might have noticed in your second lab where you actually compressed a spring in that spring gun. The more you compress it, the greater force you need to apply, right? So this time, with displacement, our force is not constant. In fact, this is the graph that represents the force versus displacement of the spring. So this is the equilibrium position of the spring, where there is no force and no displacement. The more you compress it or the more you elongate it, the greater force you need to apply. Yeah? Earlier, when we did the work formula, we said we assumed that the force would remain constant. so over the displacement. This is a case where a force is actually varying. The value of the force is changing constantly. So we get the work done in this case by taking the area under the curve. This red line is the curve. I know it's a straight line, but we just have this expression area under the curve. In this case, it's the area under this red line until the positive x direction. So all this shaded area, yeah? If this x is the displacement, this x here, then the work done is the area that is shaded, which is half base into height. So that means 1/2. The base is x, and the height is the force. By Hooke's law, this is negative kx. So negative kx times x is going to give me negative kx squared. The negative sign is not important here. If we just take the magnitude of this, then the area is equal to half kx squared. Yeah. So the negative sign just tells you which way the force is applied. Okay.